discuss some more questions. So let me start the session by sharing the screen. So I think the screen is visible. So let's start with question number 1. Let's wait for a few more minutes because there is nobody in the call, so let's wait. Okay, so let's continue. So question 1 is define Kumar extension and give some example of Kumar extension. And the B part says what is a primitive root of unity. Let's say primitive, I should add primitive nth root. And does Q and F7 contains a primitive nth root of unity for all n less than equals to 5? This is the question. This question basically gives you an idea that does all the time we have all primitive nth roots of unity, and which fields have those property? Like, can we say all time any field can have the primitive nth roots of unity? So does this give some idea that not all the time fields can obtain all primitive roots? Okay, so solution. So you can, maybe we will wait for a few minutes and by then you can recall the definition. Alright, so suppose we have any positive integer and f be a field, let's say, such that it has two properties. So in order to define these extensions, Kumar extension, we need to fix certain property on the field. So certain property on the base field. So this is my field such that either characteristic of f is 0 or characteristic of f is a p prime course it's prime, such that P does not divide this n, this fixed n, which we are fixing, let's say fixed n, and it should not divide that n. Then we say extension K over F. So an extension K over F is a Kummer extension if K contains, so okay, so in fact, maybe before that, if I will put some more condition on the base field. F contains a primitive, it's important, primitive nth root of unity. So only base extension should, whenever it has some primitive nth root of unity, then only we talk about whether that extension of that field is a Kummer extension or not. So by default, that should contain this. And K over F is n moreover xn minus a. Or maybe I should write, and K should be there, and K is the splitting field of an irreducible polynomial of the form x power n minus a for some a in F. So here there are several, there are several assumptions on that field. So in general, so if you see, maybe notation is not that good. So if you see that there are many condition on this extension in asking that whether it is a Kummer extension or not. So one thing is important, that this field should have this property. So we say that F contains this property with let's say this is my property star, with F satisfies star. So F, first of all, F should have this property, one thing. Another, it should have a primitive nth root of unity. This is a second property. Third, the given extension had the same number n, whichever nth root of unity it contains, and it should be the splitting field of certain irreducible polynomial of this form only. So there are several conditions on the field in order to say extension of given field, whether that field is a Kummer extension or not. Now, of course, this definition does not give much hint, but we will see some certain equivalence later. So let's reduce some example in order to understand the definition. So example, maybe for a minute you can think of some example, then we can discuss. Hello?
Hello,
Yeah, so
madam.
yeah, so till what time like you have joined and you were waiting for some time, right?
2:57.
But I did not see you waiting in the list. Anyway, so let me just repeat. So I will quickly go to the. So I have just started maybe 5 minutes ago. So I'll repeat. So question 1 is define Kummer extensions and give some example of these extension. And second question is what is a primitive nth root of unity, and suppose we take Q and F7 to be two fields, then do they contain nth root of unity for n less than equal to 5? So this is the question. Now if you see what are the Kummer extensions, and if you recall, then first of all, if I want to say given K over F is Kummer, then this f has certain properties. So the first property is that either it is characteristic zero field, or the prime field that we are looking, that should not divide a fixed integer n. So that integer, we will look at what is that integer. So it should not divide a fixed integer n. Now we say an extension k over f is Kumar if this is the first property, that f contains a primitive nth root of unity. So this f not only satisfies the star property, but it should also have a primitive nth root of unity. So this is that n which the characteristic should not divide. So these two things are same. Moreover, the extension should be degree n, and it should be seen as a splitting field of an irreducible polynomial of this form. So if you notice, there are various properties on the base field f and also on the k. So property star should be there for f. It should contain a primitive nth root of unity. This is property 2. Now the extension should have degree n. This is the property 3. And not just that, it should be a splitting field of some irreducible polynomial of this form only. This is property 4. So these all four things, if they are there, then we say extension is Kumar. Is this okay?
Yes. The
So,
definition of Kumar's
sorry?
extension. Okay.
Okay, so if you see this is a definition, correct definition, then can we see some examples? Before constructing extension, you should have the base field should have some primitive nth root of whatever degree extension you want to construct. It should have that root of unity. So let's say we want to construct a degree 2 extension, and we want to say that is a Kumar extension. So very first thing, your base field should have a primitive 2th root of unity, square root unity, let's say. So what are the primitive second root of unity, let's say?
Second, -1.
Yeah, so -1 has order 2 in f. Let's say, what is your base field f? What are you choosing? Let's say we choose q. This is our f. So it has -1, right? Hello?
Yes.
And -1 is a primitive second root of unity. That is also correct. Huh? Huh. Huh. So therefore, -1 is a primitive second root of unity. Now we can think of constructing a Kumar extension of degree 2. It says that in order to construct a Kumar extension, your base field is characteristic 0. That is correct. It is containing a primitive second root of unity. Another property, it's correct.
Yes.
Now you want to construct a extension of Q such that it should be a root of the extension that you construct. Then it should be constructed through a splitting field of degree 2 polynomial like this. It's degree 2, n is 2. So how to write now this extension which has this irreducible polynomial? Irreducible polynomial. How do you find the a? This is the only thing left.
A equal to -1.
A equal to -1. Well, if a you choose -1, then x square plus 1 is this. Yeah, is this irreducible first of all?
Irreducible over Q.
Is it irreducible over q?
X is quite plus 1.
Right, because its roots are plus minus I. That does not lie in q, so therefore it is irreducible. So how do you write your extension of q which has degree 2, and this is the irreducible polynomial for your extension?
Q of
Now,
5.
Q of I, exactly. So this is the extension, which is a Kummer extension. Now, if I say that you choose any A to be non-square element, so you see that -1 is not a square in Q. That means you cannot find any element such that A square is -1. Same thing I'm saying, you take any element in Q which has whose square root is not in Q. Like 4, its square root is 2, it is in Q. But I'm saying you choose that element whose square root is not in Q, then all such elements, Q root A over Q, gives you a Kummer extension. Is this okay?
So A is not a perfect square, right?
Yes, A is not a perfect square. Exactly, that is the case. Yes. So I think now this case is fine. Now we know that how to see Kummer extension, how to develop example of Kummer extension. So if you see, there are several things one has to keep in mind in order to construct a Kummer extension. So in general, this is not very easy thing. So soon, therefore, we will see some criteria to get Kummer extension. Lot of examples of Kummer extension. Anyway, so going to part B, it says what is a primitive nth root of unity, and does our field Q and F7 contains a primitive nth root of unity? Yeah. What is the definition for primitive nth root of unity?
So zeta power n must be 1 and zeta
Okay.
power I not equal to 1 for 1 less than or equal to I less than n. Then such a
Sorry.
I is called.
You
I
said
is
something?
when we
I'm sorry,
say
Chris.
psi not equal to 1, we have to mention psi not equal to 1 also.
Yes, yes. Right. So therefore, xi is the primitive root of exactly. So such a xi if you have, which is not equal to 1, none of the powers of xi is equal to 1, less than n. Only the least power which is giving me 1 is n. Then we say it is primitive nth root of unity. Okay, so my question is, suppose we fix Q and F7, then these are two fields. Does they contain nth root of unity for n less than equals to 5? So let's look at Q here, F7 here, and we have n here. Okay. Suppose we take n equal to 1. F7, remember it has elements 0, 1, 2, 3, 4, 5, 6, modulo 7. The operation is mod 7. Q anyway we know it. So for n equal to 1, what is the primitive first root of unity?
That is 1.
That is 1. So anyway we will write somewhere. Okay, it contains. So 1 is there, which is xi. Here also xi is 1. Right? For n equal to 2, what are the primitive roots?
-1.
-1. Does -1 belongs to F7?
-7, which is 6.
Exactly. -1 is same as 6, and which is in F7. So again we can say that it has a primitive root. This is my xi, and -1 equal to xi is anyway in the Q also. Let's look at n equal to 3. So here what are the primitive roots?
Omega and omega squared.
Omega and omega square. So, well, omega and omega square. Yes, omega and omega square are primitive third root of unity.
2 cubed.
Sorry.
2 cubed is equal to 8.
2 cube is equals to 8, which is
Which
1
is
mod
1.
7. Right. And 2 square, if you see, that is 4, which is not equal to 7. 2 power 1 is 2.
3 is the
Again,
smaller power for which.
yes, 3 is the smallest power. So xi equal to 2 is a primitive third root. What about here, xi?
Because those two are complex numbers which are not in cube.
Yeah, so therefore you cannot get it. So therefore here it is empty. Here is no element in cube which is a primitive third root of unity. If we look at n equals to 4, so if you, in general, if you look at what are the x power 4 minus 1 equal to 0, this should give you the roots of fourth roots of unity, among
I
them
and
which are,
minus I.
yes, I and minus I are primitive. Maybe I will stick to n equal to 4 only. So till n equal to 4. What are the inside F7? Does it have any primitive third root of unity? Let's look at 0. If you see 0, 0 is never the case. If you look at 1, 1 is never the case. If we look at 2, 2 power 3 is 8. So it's not a primitive fourth root of unity. So this is not, this is not, this is not. Let's look at 3. 3 square is 9, which is 2. 3 cube is 4.
27. 6.
Sorry. So if we look at 3, that is 3 square is 1. Sorry, 2 mod 7. And 3 cube is 9, which is 27, which is how much?
Mod 7 or mod 9?
Mod 7. We are looking
Mod
at
7,
modulo
yes.
7. Yes. So we
3
have
is also
3. Yeah.
4 cubed is coming, I think.
So this is 3. This is 6, right? So clearly you will see that anyway you must know that if you have F7, then
So we can maximum go up to 4, right?
yes, right. So if you see, what are the elements inside F7 which has order 7? Can you find that?
4.
How?
4 cubed
4
equal to
cube
1.
is 4 cube is 1. Yes. So therefore it cannot be primitive fourth root of unity, right? Same with 2. 2 is also not, because 2 cube is 1. Again, it's not a primitive fourth root of unity. 0 and 1 anyway not there. So the possibility is either 3 or 5 or 6. You agree? If you check from here, 3 power 5 is nothing but 12 mod 7, which is 5. 3 power 6 is 15 mod 7, which is 1. So again, if you see, it does not have primitive fourth root of unity. I mean, I should say till 3, 1, 2, 0, 1, 2, 3, 4, they are not the primitive fourth root of unity. But you can check whether 5 and 6 are there. Now, if I look at Q section, then primitive fourth roots of unity are I and minus I. And those both are not in Q. So again, the set is empty.
Excuse
So,
me.
yeah, so this
We have
somehow
checked
this
3 squared, 3 cubed, 3 power 4. What is the
yes,
need to check 3 power 5?
3
Because
power 5 is 5 mod 7.
no, Because it is we are finding only n is equal to 4.
Yes.
Then why do we find 3 power 5, 3 power 6?
Yeah, there is no need, of course, there is no need. As you said, there is no need. One can check for 5 and 6 also. Check. Yeah, there is no need. So I think then they just give the idea that not all the time fields have roots of unity. I think it may or may not have. I'm not sure. Maybe F7 does not have primitive fourth root of unity. So it just seems like even Q does not have primitive third. From third onwards, it does not have primitive roots of unity. So fields may not have in general roots of unity, but this idea will be helpful in constructing the extensions of field. So suppose you don't have roots of unity, you add up the roots and then you will get an extension. So this is just to see that. Okay, so question 2 is about given equivalent statement to say a finite extension is a Kumar extension. So by definition, we saw that it's very like it's too much to ask in order to say extension is Kumar extension. Your base field should have many properties. Your extension should have many properties. But can we find an equivalent statement which is simple enough to check a extension is Kumar or not? Yeah.
Cyclotomic extensions.
Cyclotomic. It's given in the results, one of the results, that some statements are equivalent in order to say a extension is Kumar extension.
Kumar state extension.
Yeah, so if you see, let's sorry.
Cyclic extension is connect.
Exactly. So we saw that if we have, let me write the statement because the statement is important. So you know when we have extension to be Kumar, we need base field to be either characteristic 0 or characteristic P such that P does not divide some fixed integer, and that fixed integer is nothing but our degree of extension. So K over F some such that F has primitive nth root of unity. So then we say Kf is Kumar. This is a Kumar
The
extension.
dimension of K over F is N. Not needed.
Yes. Yes, that will be needed. Such that K over F is N. That is degree N extension. Yes. That N is related with this. Yes. So we say a degree N extension with base field containing primitive nth root of unity with either characteristic 0 or P does not dividing N. Then we say, yes, then K over F is a Kumar extension. Kumar means it should be seen as a splitting field of some irreducible polynomial of the form x power n minus a over of course f. So this statement is equivalent to saying that K over F is a cyclic extension. Well, if you remember, what when do we say an extension is cyclic?
It is Galois, and the
Yes,
corresponding Galo group is cyclic.
exactly. When the Galois group is cyclic and the extension is a Galois group. Yes. So, thus the equivalent statement is now very nice that in order to look at a Kumar extension, it's enough to look at the Galois extension whose Galois group is cyclic. So there are now several examples to see when whether an extension is Kumar or not. So can you find examples now? Yeah. There are several, right? Like Q root 2 over Q, Qi over Q, Q omega over Q, where omega is primitive third rate of unity. Right, all such examples are nothing but your Kumar extension. However, there is some non-trivial example that I will write, which we will discuss maybe later. So, example, non-trivial example is you take the primitive pth root of unity where p is a prime and take over q. All right, so base field has that same property, right? So now if you try to see, I mean, maybe we will see this later. This is a non-trivial example of Kumar extension whose Galois group is Galois of q zeta p over q is nothing but fp cross. And we will see that why it is an example of Kumar extension. So I think we will discuss this in brief. Why this is an example of a Kumar. That means why one has to say that why it is Galois first of all. I think Galois is easy to see. So can you argue that why it is Galois?
So x power p plus 1 that volume, x power p minus 1.
Yeah. So if you
Degree
see x power, is this irreducible polynomial?
So this is, or you start with x power p minus 1 plus x power p minus 2.
Yeah. If you see the polynomial is like this, right? So then we know that since zeta p is a primitive root of unity, so therefore this should satisfy this polynomial, and we know that by Eisenstein criteria this is irreducible over Q. So clearly the degree is matching with the order of the group, right? Fp cross means, I think I should write, this is Z by Pz cross. That means Z by Pz is a field. You take out the
P
zero
minus.
element. Yeah. So it has p minus 1 element, that is correct. And your degree is also p minus 1, that's also correct. And also you know that now it's also a Galois extension. Why? Because it's a splitting field of a irreducible polynomial of this over Q that you know now. And it's a separable in fact. This is a splitting field of a separable polynomial moreover. Why? Because you know that all the roots of your polynomial are zeta 1, zeta square, zeta p minus 1. These are all distinct roots of your polynomial that you know. So therefore one can say that this extension is also Galois, and somehow we will see that why this group is a cyclic group. That is important. Okay, so we will discuss this later. So these are certain example. Knowing the extension is cyclic is enough to say that extension is Kumar. All right. Now Question 3 is the polynomial x power n minus 1 equals 0? Maybe I should say is the polynomial separable over finite field fp if p does not divide n. What about if p is equal to n?
If p equal to n, I think it is separable.
Well, you are saying when p equal to n, yes, then?
Because when p equal to n, its derivative is 0.
Okay.
So the derivative has only 0 as its root.
Okay, then what can you say?
So therefore, they have no common root. F of x 0 has 0 is not a root of f of x.
Well, you cannot argue this way, right? We discussed this part last time that if your f and f prime, you want to check the GCD of these two polynomials, then both have to be non-zero. But your f prime is entirely zero polynomial. Your f prime is just the zero polynomial entirely. That means every x, it is just zero. So therefore, you cannot apply this criteria to check whether f and f prime has common roots or not in order to say the separability. So this idea is not correct.
But in the video lecture, I think they have done it like this. F of x
No,
is x
no.
power p minus 1.
No, I
Derivative
must have used the. No, I don't
because
think so. This
0 is the only root for f dash of x, but 0 is not a root of f of x.
well,
That
I can use that fact. I will say. Okay, I will say. So if I have done that, then there should be something wrong. But I believe that I have not done this. But let's see. If I have done, I will correct now. So if your okay, let me write. If your fx is x power p minus 1 for, let's say, your let's say x power n minus 1 where p does not divide n, let's say. You know that f prime is nothing but n times x n minus 1. That's it. Now you know your polynomial is not 0 because p does not divide n. Right? You are using this fact here in order to say your polynomial is not entirely 0. Therefore, the roots of this polynomial n x n minus 1. What are the roots? That means if I ask you what are the x for which this equation is 0, it's just x equal to 0, right?
0.
Yeah. So only roots of f prime is x equal to 0. However, roots of f is nothing but which are satisfying x power n minus 1 equal to 0. So x equal to 0 cannot be a root of f. That means the roots of f and f prime, they are not at all common. Not at all common. So we can use this criteria of derivative f and f prime are co-prime only when both polynomials are non-zero. I think this we discussed. Anyway, so if I have done wrong, so you can clarify now. So therefore, this says for p does not divide n, then we can say your f and f prime have no common root, and therefore f is separable. It's very important fact. That's why I discuss this part now. Is this okay now?
Yes, this is okay. That is
All
the
right,
p
but
does not divide n.
yes, if p does
They have
not
no
divide,
common factor.
yes.
So it is
What if, yeah? So, but what if p equal to n? So you're so important that your characteristic of f is p. This is what we are saying. P. Now, one of course one cannot use the criteria that we use, but can we say something else? So if you,
Here also
yeah,
f dash of x is 0.
yeah, if you see here f dash is p x p minus 1, which just becomes entirely 0. So we cannot say anything. We cannot say anything. So from f prime we cannot say anything, but there is something which is given for x. X is fx is x power p minus 1. If I ask you what is x minus 1 whole power p, can you expand it?
In characteristic p case, they are equal.
They're equal, right?
Hmm.
Yeah. So I think this I said. So whenever you have p here, and wherever your characteristic is also same, in that case you can always take the power, and you can say the roots are multiple. So if you see now, f has multiple roots, and for separability, you should have all roots should be single roots, no multiple roots. So therefore, in this case, your polynomial is not separable. So here, I will write here equal to n implies x power p minus 1 is not separable over finite field fp. In fact, any field of characteristic p. So is this thing now clear, right? This is clear.
Okay, f of x has multiple roots, I agree. Hence,
Yes.
x power p is
Sorry.
not a multiple. We are not
Yeah.
even
So
going.
you're,
We are not even going to first derivative,
yeah.
because
We don't need. We don't
it
need.
has multiple roots.
Exactly.
Because
So ours. Hmm.
the multiple roots means f dash of x and f of x, they have common factor.
Exactly. That you can say. But you
Yes,
cannot say from f derivative because your derivative is entirely 0. That you cannot say from there. But you can check the property from the polynomial itself.
that is, it has a multiple root, therefore not separable.
Yes, not separable. Exactly right. So therefore, in this case, it is separable. In this case, not separable. So therefore, if I try to extend, let's say I will try to write an extension by writing the roots of this polynomial, then you cannot say the extension is separable. So this is just the idea to say that this polynomial is important with the characteristic. All right, so we will go to now question 4. Here we are recalling certain fact. We just recall that if a given extension is Kumar, that is if and only if extension is a Galois extension and its Galois group is cyclic. So what is the condition on the base field in order to satisfy this above result? It's just a previous question only. I think I'm just recalling the previous things.
That is, either the characteristic of the field is 0,
Yes.
or if it
So
is p, then p does not divide n.
exactly. So I'm just repeating these things several times just because they are very crucial, very crucial. So, so this K over F is Kumar if and only if K over F is Galois and Galois group of K over F is cyclic. This is true only if K over F is some n, and for that n, the characteristic of field, if it is prime, then P should not divide n. Or characteristic is 0 and degree can be anything, we don't care. This happens and F should have primitive nth root of unity. So I'm just repeating several times just that
Yes.
it will be clear. Yes. So base field have should primitive roots should have degrees should be this such that P does not divide n or it is 0. This is the additional things just to say your if and only if condition. So if somebody asks you Kumar is a if and only if Galois, so it's not always true. Under some assumption on the field, then only it is true. All right. And question B says, can we realize K as a splitting field of some polynomial? So we have written that if it is Kumar, then it is Galois. And Galois group is cyclic. Now, we also know Galois extension is same as if your extension is a splitting field of some separable polynomial over the base field. Yes. Can we realize the given field now? Suppose it is Kumar and Galois. Then can we find a polynomial whose splitting field is K? And can we determine its roots? It's very simple. It's all around the definition. It's everything around the definition. Yeah, for which polynomial can we say the given extension is a splitting field of the separable polynomial? So there are so crucial things that are going on behind. So I just want to discuss. That's why I put this as a question. So if you recall the definition of Kumar extension, it is an extension with satisfying all base property, this which we have written. Our field should have this property. And K is a splitting field of, if you
X
remember
power
definition.
n minus a
Yes, it's a splitting field of,
for some a in F.
yes, and moreover irreducible. It's written irreducible polynomial x power n minus a for some a in base field F. These things are known from the definition of Kumar extension. So we got something as a splitting field. But in order to say it is a Galois, it should be splitting field of a separable polynomial. Now, given this polynomial, can we say it is separable? Yeah. So if you see the roots, what are the possible roots?
Okay, what we have seen before the previous problem.
Exactly. So it boils down to the previous problem saying that x is, the roots are nothing but a power 1 by n, a power 1 by n times I, or 1 by n times I square, or 1 by n times I power n minus 1. And why I'm saying all the roots are distinct because the polynomial x power n minus 1 is a separable polynomial. Why it is separable? Because of these two conditions. Because your roots are how you have added the roots. You have just taken x power n minus a 0 implies x equal to a power 1 by n times xi k, where k is 0 power 1 to up to n minus 1. These are the primitive roots of, all the roots of unity. And you multiply with a power 1 by n. That will give you all roots of your polynomial. But important is all the roots are distinct of this from this polynomial because this polynomial is separable. Why? Because the fields have these property. So there are several things going on. The important is this polynomial itself gives me that being k is a splitting field of this polynomial implies k is a separable and normal extension over f. This is okay, right?
So Galois.
Therefore, Galois. Exactly. So the polynomial for which we want k to be as a splitting field is this polynomial x power n minus a for some a. This is okay, right?
Yes.
All right. So these are the key details, and now we will go to question 5. So let's say k over f be a finite extension and alpha is an element in k. When do we say alpha is expressible as radicals over f? Yeah.
And alpha is expressed as the help of those four elementary operations.
If alpha is, okay, let me write. So we say alpha is expressible as radicals over f if, yes,
That definition. If there is a tower,
well, if I ask you the definition only, let's say, okay, that is the equivalent criteria. We will go to that
okay,
also.
okay.
I will write that also.
So alpha can be expressed using the operations and the radicals of f.
Exactly. If alpha can be expressed as combination of plus, minus, multiply, divide, or radicals, you understand, right? Expresses combination of these over elements of f. That means, let's say if I have f, let me try to understand this example definition. Suppose f is q, and I want to check whether root 2 plus root 3, whether, let's say, how do I write? Root 2 plus 5 by 3 plus root minus 1. Are these example of elements which are expressible as radicals over q? This is what we want to ask.
Yes.
So this element, let's say root 2 plus root 3, we say that radicals are allowed. Radicals means you can take powers of that element and you can get into our polynomial, into base field, which is q. So this element, if you see, if you raise its power, it is in q. Therefore, this is a radical element. So root 2 is a radical. Now, root 3 similarly also, it is also in q. Therefore, root 3 is also radical. And you are saying it should be expressed as combination. So it's a radical, plus is an operation of combination. Therefore, this also element is expressible. So this is also expressible as radical. So this is the basic definition now. We understand now what are the example, and also similarly, this is also an example of element which are expressed in terms of radicals. Question is I expressible over Q? So B part is I expressible, imaginary number I expressible over
So,
Q?
answer is no.
Answer is no, but I'm saying answer is yes.
I is expressible over q. That is square root of minus 1.
Yes. So if you see root 1, this is nothing but I, right? So radicals means that some power of that element should lie in Q. So clearly this power is minus 1, which is in Q. So therefore I is expressible.
What you have written above, plus square root of minus 1.
Yeah, so I said it is expressible. Yes.
Yes.
So
I
is
is
there any doubt?
expressible over A or q.
Yeah, it is expressible. Do you agree?
Yes.
Okay. All right. So now we know somehow the definition of expressibility. Is there a criteria to check whether element is expressible as radical now? Now what you said earlier, I want to discuss that. So as you said, let me just recall. Um, so alpha is expressible as radicals over f. Now this is in field theoretical language. Over f if there exists a tower, as you said, of fields such that, let's say
First,
suppose your tower is...
can we define when an extension is simple radical or radical extension, from which we can define when an element is expressible?
Yeah, that will come in the definition. Yes. So we will see. Yes.
Okay.
So they resist a tower of field such that you have F naught contained in F1 contained in Fr, and the final field should have your alpha, whichever you are asking for. Okay, such that first of all, this anyway, this I have written here, alpha is in Fr, the final field extension. And second is all your extension, corresponding extensions, Fi by Fi minus 1. That means you take F1 by F naught, F2 by F1, Fr by Fr minus 1. All such extensions should be radical extensions. Now, one has to know what are radical extensions. So, can you recall that?
Radical extension.
Yeah. Yeah. When do we say an extension is radical?
So there you will get simple radical extension, right?
Yeah, so that means your extension k is f times some element a, let's say a, such that a power n is in f for some n. All right, so if you see example, let's say if you want to check which extensions are radical extensions. So if I say k q root 2 over q 2 power 1 by 3 over q omega over q, all such where omega is third root of unity, all such are examples of, all are examples of radical extension. This is okay, right? So this is the another definition. However, this is very not very simple, like it's difficult. So if you can see the radical itself, the things of radical, it's not simple. Like whenever we want to check an element is radical, expressible as radical, it's not. Sorry.
This is the definition of a simple radical extension.
Yes, this is the definition of simple radical extension. Yes. Right. All right. So important is knowing an element. Checking through this tower is not very easy, but soon we will see that why these extensions are useful through Kumar extension. So next question is says that are radical extensions related to Kumar extensions, and if they are related, how they are related. So suppose you have k over f is Kumar, and suppose you have k over f, k prime over f prime is let's say radical. Which one implies or which one is related to the other? Can you see some pattern, something? Yeah.
But k dash is k of zeta, and f dash is
If k dash is f
k
dash
of
zeta.
k dash is k of.
Sorry, I'm not getting what you are saying. Can you say it again?
What is your question?
Yeah, so there is some connection for this radical extension and Kumar extension. So I want to say whether can we build some connection, because reading Kumar extension should not be a waste. I mean, we should be able to say something, because we are trying to see, after all, this whole theory of Galois is just solving polynomials by radicals.
Yes.
So therefore, this and this radical extensions also, if you see, there should be one idea that this extension should give something or the other with solving the polynomials by radicals. So now, question is, why Kumar extensions came into idea? Of course, we know that Kumar is same as Galois extension with Galois group is cyclic. Therefore, and we know very nicely what are Galois extension. So, therefore, we know now Kumar extensions. I'm saying Kumar extensions, how they are related with the radical extension. If you see the definition of a radical extension, it is just you have to generate by a radical element over the base field. Now, suppose we know that, then can we say something? If you look at radical extension, like q root 2 over q, if you say, then you know that this root 2 is an element whose square is in q. Therefore, root 2 is a radical element. Therefore, your extension is a radical extension. Is it Kumar? You checked, right? This extension we saw through Galois also, Galois theory, that it is a Galois extension. Galois group is a cyclic group of order 2. Therefore, it is Kumar also. So I'm saying that radical and Kumar are same. Once you have your base field having that same property, that characteristic of f is a 0, or characteristic or characteristic of f is p, and p should not divide n, where n is the extension degree. Moreover, f has a primitive nth root of unity. So why this is enough? Because the remaining thing which you are getting, so in order to say it is Kumar, the remaining thing is that your K should be a splitting field of x power n minus a. But what does that mean? It just means that x power n minus a implies that x equal to a power 1 by n, right? So somehow it is saying that you are able to get a for which a power 1 by n, and its power is in element in Q.
Radical.
That means a power, yeah, so it's a radical element. And the remaining elements are nothing but the xi. So if you see, the remaining roots are nothing but just the primitive roots of unity. Those are also radicals. Why? Because the power n equal to 1. So therefore, your extension is being obtained by adding just the radical elements. So therefore, radical is same as Kumar once you have these things. So once you have, your field has this property, remaining property of definition of Kumar will say you that it is radical. And radical anyway tell you that it is Kumar extension. So anyway, so
The fields are same or different? Here you have written K over F, there K dash over F dash.
yeah, so I think I should write K over F. Same thing. Yes. So the same extension become a radical provided you have these properties on F. And you know, the primitive roots of unity implies that somehow these are contained in your field. And therefore, you just need to take the primitive of that element only in order to generate your extension. And that will give you just the radical extension. Once you're assuming that your elements, your field contains primitive roots of unity, then the roots of unities are anyway in your base field. So in order to take the roots of your polynomial, you just have to take the radical of your element. And that will give you the radical extension. This is okay, right?
Okay. So every time we'll have to check these conditions.
Exactly.
The field is satisfying all these conditions.
Correct. So these are very crucial. These are crucial. Yes. So once you know this, then you know that radical is same as Kumar. Good. So therefore, they are not waste. I mean, reading Kumar is not waste, or reading radical is also not. Somehow they are related, and whichever you find more easier, use that in order to say something about the other. Yeah. So okay. Now let's go to question number 6. It says that let K be the splitting field of x cube minus 2 over f7. So is K over f7 a Kumar extension? Now recall the definition and see, or recall the equivalent criteria to see whether it is Kumar or not. I will pause for some time. You think.
So you want?
I want to check this extension to be a Kumar or not, where K is the splitting field of polynomial over f7.
Now we are going over to radicals and then check whether it is a radical extension.
Well, you can check. If you want to check, you can check that.
Or you are expecting direct verification.
Well, I feel like you should do it through definition only, and maybe through the criteria of Galois. So first of all, your very first thing is checking everything about finite field, that field, sorry, the base field.
Now we'll have to check whether it is separable. That polynomial x cubed minus 2 is separable over f7.
Okay.
Then k over f7 is going to be Galois.
Okay.
Then we can check for cyclic also.
Yeah. So there are several things to check. Yes. So let's go by definition. Okay. Everywhere you will see whenever Kumar is coming, you have to check several definitions, everything. Yes. Yeah. So first of all, we want to say K over F. What is the degree of this extension? So suppose you are having K is the splitting field of F, F7, where Fx is nothing but x cube minus 2. What do you say about this degree of this extension?
First check whether this is irreducible.
Okay, let's check that. So does it have F7 is nothing but 0, 1, 2, 3, 4, 5, 6 modulo 7. Now, if you see, do you have any x which satisfies this? Yes.
1 cube not satisfied.
None of them. Huh? So 0 is okay. This is has no linear factor, but that is not enough to say that it is irreducible, right? Yeah. So what are the, if you see what is 2 power 1 by 3, 2 power 1 by 3 um, omega, 2 power 1 by 3 omega square. These are the roots, right?
Yes.
Now, if you check, is there an element having a cube root of unity inside this mod F7?
I think none.
There is none. Huh? So then what can you say about the irreducibility of the polynomial over F7?
Or shall we use the instant criterion for this?
Sorry.
Irreducibility using Einstein criteria.
Yeah, so you have to check your if your fx is same as gx dot hx, where g and H are having degree of G is, and H has to be greater than equals to 1. That means it can happen that your one is the linear polynomial, other is a quadratic polynomial. Or it can happen that all are linear factors. These are the only two possibilities. Now, since you check that there is no root, there is no element in F7 which satisfies this property, so therefore linear factors are not there. But at the same moment, this you said that if there is no such linear polynomial, then you have to check whether quadratic is there or not. Am I confusing something? Let me think. Okay. Hmm. Well, in order to say it is a Kumar extension, first of all, we need to check that F7 should have a primitive root of unity. Huh?
Yes.
So let's check that whether it has a primitive third root of unity or not.
3.
Huh. So
Sorry, 2.
2 is a primitive third root of unity, right?
Yes.
So Fx is x cube minus 1, and then you say, let's say f prime, and then f prime is 2 is nothing but 7, which is 0 mod 7. So therefore x equal to 2 is a primitive root of unity. So it does have a primitive root of unity that we got. So first property is satisfied. This is the primitive third root of unity. Now, if you see that, does it have a linear factor? Because you see, when you are trying to split your polynomial, so you are trying to see it is like this.
Yes.
In our case of finite field, this does not make sense, because omega is nothing but, for us, it is primitive root of unity, which is x equal to 2 now. So first of all, x cube minus 2 equal to 0, it does not have a linear factor that you check. Therefore, its roots are like your, so therefore you can see clearly that it is irreducible, because if it is reducible, it should be either reducible to linear factor times quadratic factor, or it should be completely factor into linear factors.
Yes.
And you said none of there is a possibility, as you said, you checked that. Therefore, given polynomial is irreducible over f7. You can also check through f prime in this case, because in this case your 3 is not co-prime. This is a co-prime to 7. Your f3 is not entirely 0. So clearly in this case x equal to 0 is the only root, right? So for separability, you can check in this case also that anyway it is given that it is a splitting field. You just need to check the separability. So if you can see the derivative, and that is 0 only when x equal to 0. So that you can see now clearly that those roots are not with the roots of f. Therefore, it is a separable, and therefore your extension is a Galois extension, right?
Yes.
So the degree is 3 that you got to know. And it is also and if degree is 3 and it is a Galois, then what could be the Galois group then?
Because it is a prime order, therefore cyclic.
Exactly. Therefore, it is cyclic. So therefore, it is a Kummer extension that you got to know. Is there any other way to see that it is a Kummer extension or not? Yeah. Other criteria was just the definition of that. You try to see through definition. So first thing we saw that it has a primitive root. Huh? So therefore one condition is there. Your degree of extension is nothing but 3, which does not divide the characteristic of your field. Characteristic of your field is 7.
7.
This property is also satisfied. Remaining property is what? That there should be a separable, there should be an irreducible polynomial of this form such that your k is the splitting field of this polynomial. Is this okay?
It is directly given.
Yeah, so everything is given. So therefore it is by yes. So by definition it is a Kumar extension. Yes. All right, so let's go to question 7. Are radical extensions related to cyclic extensions? So I've been asking these questions so frequently just to say that whatever we have studied, they all are interrelated.
So they are equivalent.
So somehow we want to say it is equivalent. So you see, let me draw a picture now. We have here it is Kumar extension. Here we have radical extension. And here we have cyclic extension. So what do you say? You know, we have discussed this part. This is equivalent under some condition, Can we say something here, same thing, something here? Yeah. It is just the definition, right? That your Kumar extension is same as cyclic extension, right? This is the equivalence that we developed. That this is also equivalent, again, in the same condition that suppose you say K over F is this is the extension which you're talking about, then the only property that you need is characteristic of F is 0 or P, having suppose the degree is n, then P or P should not divide n, where characteristic of F is P, and your F has some primitive nth root of unity. Nth root of unity. The same condition here also requires, and the same condition will give you that they are also equivalent. So somehow Kumar extension, radical extension, cyclic extension, whichever you feel easier, you can develop provided you have these property on the field. These are crucial. These are important. This is okay, right? Okay. Now, is every radical extension a cyclic extension? So, you know, every question is answered within this picture. If you see carefully, is every radical extension a cyclic extension? So if you see carefully, we have written certain this star property. If star does not hold, then never, then this radical and cyclic are no longer same. No longer same. So can you develop something which has cyclic, maybe radical not cyclic or cyclic not radical? Can you say something? So you see, whenever you have a radical extension, then you can make it as a cyclic if you have these assumptions. Huh? So it says that under these assumptions, these two things are same.
Cyclic always implies radical extension.
Cyclic always implies radical extension. Yeah, correct. You're right. Well, if you say that, I think the answer is just itself that radical is same as cyclic if you have this condition. If you fail this condition, then we cannot say anything in general. The answer is uh, as long as star holds, radical is same as cyclic and cyclic are same. But if either of them fails, we don't know. Nothing can be said. Okay, so let's go to question 8. What are cyclotomic extension now? I mean, there are so many extensions, so one has to remember the definition. It's difficult. So what are cyclotomic extension? So radical extension means you have to write a radical. You have to find the polynomial x power n minus a and add its roots to the to your base field, where field has some root of unity. Now, if you see cyclotomic extension, that polynomial will be very special now, not just x power n minus. Yeah, so your polynomial is x power n minus 1 then, not just x power n minus a. So one's definition is, so let n is greater than equal to 1 be an integer. And again, f has the property star. Now f has property star that we have written in the previous page. Then we say that if we try to write the roots of this polynomial x power n minus 1 is 0, then the roots are nothing but 1 xi square xi power n minus 1, right, for some xi, where xi is the primitive nth root of unity. And under the assumption of star, we know that this is always separable, right? The star is important. That's why I ask you this polynomial. This is separable over f because of star, because of property star, because p does not divide m or it is characteristic 0. This will ensure that it is separable. So therefore, you have to just simply add, in order to get extension k over f, you just simply add f to your primitive root. This type of extension is called nth cyclotomic extension. This is called nth cyclotomic extension. So adding a primitive nth root of unity to your extension is called nth cyclotomic extension. Now, but under the assumption, of course, this field has this property, one has to assume. This is very crucial. All the time we are having this. Now, can we say an extension is, okay, first of all, when do we say an extension is abelian?
Sorry?
Yeah, so what is the definition saying that an extension is an abelian extension?
Abelian means that Galois group is abelian and the extension is Galois. Instead of cyclic, we have
exactly.
abelian.
Exactly right. So we just need to say that the Galois group has to be abelian and should be a Galois extension. That's the only thing we need, exactly. So now, can we see some example of both cyclotomic and abelian extension? Yeah. So
Q to Q root 2, Q to
but
Qi.
no, this is not cyclotomic extension, right?
So that root 2, Q
Root
to
2 is
Qi.
so you have to write a primitive root, primitive root of unity. Unity. So this is a second, since you know that it is the fourth root of unity, I, the primitive fourth root of unity. So therefore, this
Fourth
is
vector.
clearly, yeah. So therefore, you can see this is a cyclotomic extension. However, the degree of this polynomial is not related to the degree of, not related in the sense like not equal. So your degree is not equal to 4. This is not true. The degree is 2. However,
Yes.
the polynomial has degree 4. Reason is your polynomial is not irreducible, right? All right. So now both cyclotomic and of course this is an abelian extension. Why? The abelian, the Galois group is nothing but Z2, which is cyclic as well as abelian. This is abelian. So this is an example where we can see, in fact, q omega over q, where omega is the primitive third root of unity. Also, we can say that this is also a cyclotomic extension. Yeah. And if you see what is the Galois group here, again Z2, right? The degree to extension. All right, so all these examples are to say that what are cyclotomic abelian. So important for radicals, you have to add x power n minus a, its roots. However, for cyclotomic, you have to add x power n minus 1. And there is a result which says that the Galois group of a cyclotomic extension is always abelian. Need not be cyclic, need not be cyclic. We will see that now. So is every cyclotomic extension cyclic? This is the next question. So I said in general, the cyclotomic extensions are abelian because we will see that Galois group is abelian, but they need not be cyclic. So can you produce one extension obtained by some adding primitive some nth root of unity, which is not cyclic? Yeah. So let me just recall. So if you take k cube to be q, and if you try to add q zeta 8, where zeta 8 is the primitive eighth root of unity. So I think we have discussed this part, that if you take q zeta p over p q, then this Galois group is fp cross, and we know that it is cyclic. So therefore prime will not work. 1, 2, 3, 5, 7, that will not work. And if you try to see q zeta 4, then that is same as qi. That is also, you know, that it is cyclic. Therefore up to 7, anything will not work. You have to start looking from n equal to 8. This is right. Okay. Can you follow this?
Yes.
Okay. So therefore, q zeta 8 over q, if you look at, I'm saying that this is not a, this is a cyclotomic because our field has characteristic 0. And moreover, we are adding the roots of unity to the field, that is also correct by taking a primitive root. So therefore, the extension makes sense that it is actually a cyclotomic extension. Look at the Galois group. So first of all, I have to check Galois also. Okay. Now let's look at the zeta 8, primitive 8th root of unity. I will take e 2 pi I by 8. This is a primitive because its 8 power is 1. No less than, no power less than 8, make it 1. Therefore, if you see, the elements are 1 by root 2 plus minus. In fact, all it's all primitive roots are nothing but If you take this to be xi, then xi power 3, xi power 5, xi power 7, because 1, 3, 5, 7 are the co-prime to 8. So we will have 4 primitive roots, and if you see, all primitive roots are like this, plus minus 1 by root 2, plus minus I by root 2. Simply I can take this. In fact, all primitive roots are equally good. I can take either. So if I simplify my extension q zeta 8 over q, then this is simply q root 2 comma I over q. You agree, right? Yeah. Hello?
Yes.
Yeah.
Follow
So if you agree, yeah. All right. So what is the degree of this extension?
degree is 4.
Degree is 4. Use the tower. Use the tower. Degree is 2, degree is 2. Degree is 4. Now if you see, what group can it have? The Galois group is either Z4 cyclic group, or it can be Z2 pro Z2. What do you think? What is the group?
Here you have a
Automorphisms are sending root 2 and I.
automorphism of
Yes.
order 2 only.
Yeah, exactly. You have root 2 plus minus root 2, I going to plus minus I. All have root degree 2. This is not our group. This is the Galois group. And is this cyclic? So Z2 pro Z2, is it cyclic? It's not, right? Clearly it's not cyclic because it has order 4, but it does not have element of order 4. But it is abelian. There is no order of element of order 4. Yes. However, the group order is 4. So, but it is abelian because it is a product of abelian groups. That is always abelian. Therefore, it is a abelian group.
Yes.
Therefore, it is an example saying that not every cycloatomic extension is cyclic. So, answer is no. Not every. Is every cycloatomic extension abelian? Well, answer is yes, but that will require some proof. So let me write that. Okay. I think that is given in the results also. There is one theorem. I will just recall the theorem. I'll just recall the theorem. So recall. So answer is yes, every cycloatomic extension is abelian. Yes. And justification is this result, which says that if you have n greater than equal to 1, and if you take let f be a field, which is either you take characteristic 0 or characteristic field is prime, where p does not divide them. Always try to write. If you write, no, you will remember these properties, which is crucial. And f k over f be a splitting field of x power n minus 1. This n and this n is same. Over f. This is the splitting field of f. Then your Galois group K over F is actually a subgroup. This is a subgroup of Z mod and Z star. This group is little different. This is nothing but all those elements A,
Which are primitive roots.
well, I should say, which are co-prime to n. This is something, yeah. So those A which are co-prime to n. If I ask you what is Z by 2 Z star, then what is that? Example.
Only two.
Only one, right?
Only one bar.
Only one. Let's say bar. Okay, you put bar, then I will write bar. Now, if I look at Z by 3, Z star, then what are those elements which are co-prime to 3? All right, 1 and 2 both. And of course, your A has to be chosen from 1 onwards, not 0. So you have to choose from A 1 less than equal to A less than equal to A. Okay. If I ask you what is Z by, let's say, 8Z, then what is that? So, 1, 3, 5, 7 are which are co-prime to 8. So 1 bar, 3 bar, 5 bar, 7 bar. All right. So now we know the bars. And if you also see, they are abelian, right? We have just integers. So we have just integers. So 1.3 is bar is nothing but 3 bar. 3.1 is also same as 3 bar. So they are integers. Integers commute. So this is a abelian group. And you also know that subgroup of a abelian group is always abelian. So therefore, Galois group is abelian because Z mod and Z star is abelian. Why abelian? Because elements are just integers. Modulo n, but still integers. All right. So therefore, a Galois group is always, for a cyclotomic extension, is always a subgroup of a abelian group, therefore abelian. So this is a important note that every cyclotomic extension is abelian. All right, and there is a map that one can define. You can see in the notes. So that is easy. Let's go to roots of x power n minus 1. So we know that roots of, okay, there is one important result I want to recall here. Question 10 says that recall roots of x power n minus 1 in any field form a cyclic subgroup of k. Wherever you are looking the roots, inside that it will form a cyclic group under the multiplication group. This is a very, very important result. So can we see some examples? Let's say if I look at n equal to 2, you give me some field, whichever field you feel it's nice to use. We will see n equal to 2, n equal to 3, n equal to 5, let's say 4. So which field will you choose as a k? Hmm?
Q root 2.
Okay.
N is equal to 2.
Okay, your k is q root 2, all right. Now, if you see, I want to look at x square minus 1. Now, roots of this are, what are the roots? Hmm? Roots are plus minus 1. Hmm. And this you see 1 minus 1. This is a subgroup inside q root 2 star under multiplication. Under multiplication because 1 minus 1 has order 2 under multiplication. Therefore, it is a cyclic group. This is isomorphic to Z2 because it is like 1 comma a such that a square is 1. Therefore, it is cyclic. So we see, at least for n equal to 2, things are nice, we can say. Let's look at n equal to 3. Which field? Now important, how you choose your field. You have chosen k q root 2.
N is equal to 3.
Yeah, I'm choosing now n equal to 3, but you have to give me a field. I can choose my own field. I will tell you the roots of x cube minus 1 in given your field that will form a cyclic subgroup. Just like here, we saw it forms a cyclic subgroup of order 2. We want to see whether n equal to 3 makes a cyclic group inside any field. But field, I'm asking you, give me an example of a field.
Z3.
All right, Z3. So Z3 is 0, 1, 2, mod 3. And Z3 cross is our group in which we want to see the roots of x cube minus 1. So Z3 cross is just 1, 2. Multiplication modulo 3. Now this is multiplication modulo 3. That is addition modulo 3. Well, operations are both because it is a field. Anyway, so x cube minus 1 equal to 0. Now let's look at the roots. So if you see, you are looking inside Z3 now, okay? So what are the all possible x in Z3 which satisfy this? clearly x equal to 1 is there. Huh? You know that 0 minus 1 is minus 1, which is not 0. Look at x equal to 2, then you will see x cube minus 1 is 8 minus 1, which is 7, which is also not equal to 0 mod 3. Therefore, x equal to 1 is the only root, and therefore this is just a trivial group inside Z3. Just the trivial group. If you see, if you increase your field, okay, this is very small field that 1000. But I'm saying you choose some big field, let's say Z7. And you will see 0, 1, 2, 3, 4, 5, 6. Look at x cube minus 1. Can you find what are those x in Z7 which satisfy this?
One satisfies.
Yes. Anything else?
2 also satisfies.
Exactly. What else?
3 cubed 27. 4 cubed 4 satisfies it.
Exactly. And if you see, there will be none which will satisfy.
No, madam. 4 cubed minus 163.
3. 7 nines are 63. Yes. This is 0. But if you say 5 and 6, they will not satisfy.
4 also not satisfied.
4 satisfied, right? 4 cube is 64. And 4 cube minus 1 is 63. This is 0 mod 7, right?
Yes.
So therefore it's satisfied, right?
Okay.
So 1 to 4 are the only things I'm saying. Other than that, there is no other element. No other. So you see 1 to 4, 1, 2, 4 is a cyclic group inside the Z7 star. Your Z7s have elements 1, 2, 3, 4, 5, 6. Okay. Now look at 1. So clearly 2 is the generator for this, right? 2 is 2, 2 square is 4, 2 cube is 8, which is 1 modulo 7. So therefore, 2 is the generator. It is a cyclic group inside this field. In fact, just to show you that not so Z3 looking at that, it does not have a non-trivial primitive root. Sorry, it does not have a primitive root. But Z7 has a primitive third root of unity. So in general, if somebody asks you that given a finite field Fp, you cannot answer that which primitive roots does it have or which it has. Primitive is like very difficult to find. But it says that if you take a group generated by the roots, that will be a cyclic group inside any field. Any field. This is a very, very important result. And other thing, part B says prove that a finite subgroup of K cross. In fact, this says that this group generated by roots of x power n minus 1 forms a cyclic group. Other statement says if you take any finite subgroup of any field, finite or infinite, but if you take finite subgroup, that will always be a cyclic subgroup. That is also very crucial. These two statements are very important. All right, I think we will, if you get time, then we will try to see the proof. But if not, then it's just the theory which is very important. That if you take a finite subgroup of a field, it is cyclic. If you take the root generated by, if somebody asks you that if you have a finite subgroup, in fact, that finite subgroup inside a field will be a group generated by the roots, in fact. So this cyclic subgroup is nothing but the generated by roots itself. Yeah. All right. This is question 11. It says that suppose you have a field satisfying the property star and you have a splitting field of x power n minus 1 over the field which satisfy this property, which we know that all the roots are distinct because your field has that property. So given extension is nothing but it's a Galois extension. Why? Because it is a splitting field of a separable polynomial. Separable because of the field property. First part is K over F is abelian. Why? This has been done now. I think you can recall it.
Yes.
Why? Because the Galois group of cycloatomic extension is abelian, right? Whereas Galois group of cycloatomic extension is always abelian. Therefore, one holds. Why? Because K over F is a cycloatomic extension. All right. Second says, is Galois group isomorphic to Z mod NZ for all F satisfying above property? This is important isomorphism. We are saying Galois group for any cycloatomic extension is abelian. That's perfectly fine. But is that Galois group always isomorphic to this group? This is the next question. Yeah. Well, if you see, we saw the result, recall that Galois group for a cycloatomic extension, suppose this is cycloatomic, and Galois group is always a subgroup, important, Z mod and Z star. And since we saw that this is abelian, this is how we argued that this is also abelian.
Yes.
But is this isomorphic to Z mod and Z? Is not always the case. This is not always the case. But there is, recall, there is from your theory that if F is Q, then that is isomorphic. You know, cycloatomic extension does not say that your F has to be Q. Your F has this property only. And Q is one example of that field. You can take any field, let's say FP, and you take an n degree extension, cycloatomic extension. That is also cycloatomic. Because you are taking n and P does not divide n. So example of cycloatomic does not say your base field is Q only. It can be any field. But if you take F to be Q in particular, then yes, then the Galois group of K over F is isomorphic to actually Z mod and Z star. And if you see, in fact, this is also not cyclic all the time. If you see, this is not cyclic always. Why? Look at the previous things. Z mod 8 Z star. If you see here, is it cyclic? Well, if it is cyclic, then any element should have some element. Yeah. So do you have any order 4? So order of 3, look at order 3, look at order 5, look at order 7. 3 square is 9, which is modulo 8, 1. 5 square is 25, which is 1 modulo 24, which is 8. I mean, modulo 8, I should say. 7 square is 49, which is 8, 6, 48. So 1 modulo 8. So all the orders are this, therefore this is nothing but Z2 cross Z2. It is order 4 element. It is an abelian, sorry, order 4 group. It is an abelian group, but not cyclic. Therefore Z2 cross Z2. Not cyclic. So yeah, it just says that your Galois group of a cycloatomic extension is always abelian. And what is that group? It is only known only when your base field is Q. Otherwise, it is just a subgroup of this group. This is all right, right?
Yes.
Okay, so now let's go to finding the degree of following extensions. This is important now. So if I ask you Z, let me ask you a solution. Let me ask you what is Z mod pz, it's a star. Recall the definition is all those I bar such that I and n are coprime. Can you tell me what is that?
I and P.
Yeah. N is P. For me, N is P.
For a prime number, all numbers from 1 to P minus.
Yeah, 1 to P minus 1. So 1 to P minus 1 bar. So cardinality is Z mod PZ star, which is P minus 1. And what is the generator for this group?
Generator is 1.
Well, this is multiplicative modulo T,
Okay.
right? So you have to be careful that generators will be, in fact, you see, all x not equal to 1. That will be generators. Well, there are many generators. Anyway, so it's a cyclic group. Okay. Now, since you also saw Z mod 8, Z star is not cyclic, huh? Because 8 is not prime. So recall that also. Yeah, so now we are trying to find the degree of this extension Q zeta 8 over Q. You know, in order to find the degree of this, I want to see the degree of irreducible polynomial for a primitive eighth root of unity. So, in order to see the degree, we want to find the degree of irreducible polynomial which is being satisfied by a primitive eighth root of unity. Now, I'm saying in order to know that, one needs to know certain polynomials which we call as cyclotomic polynomial. Those will help me to get that the degree. What is the degree? So let's look at that. In fact, if you look at x power 8 minus 1 equal to 0, maybe we will come back to this question, okay? We will come back to this question because I need something else, which will come in the next question. I will come. Let's go to question 13. What are cyclotomic? Because this is what we will use in order to solve the previous question. What are cyclotomic polynomials? That are important now.
That is cyclotomic polynomial of degree n.
Okay.
Say. Degree n means you have to consider all primitive nth roots of unity. So product x minus zeta, zeta varies over all primitive nth roots of unity.
Yeah, so polynomial, cyclotomic polynomial, I should say, cyclotomic polynomial Px of degree n is the product of x minus xi, where xi varies over all primitive nth roots of unity. This is okay, right? Now, if I ask you examples.
Call that degree n polynomial, cyclotomic polynomial of degree n, right?
Yes, degree n.
But actually, P of x is not of nth degree.
Yeah. So if I ask you examples, so let's take n equal to 2. So of course, one needs to know primitive roots also, all primitive roots, not just one. We need to know all primitive roots. So if I ask you, so x minus 1 is the only, sorry, x plus 1, exactly. So minus 1 is the primitive second root of unity, and therefore x minus xi implies x plus 1 is the, this is how we write phi 2 of x. Phi 2 of x, this notation for cyclotomic and second cyclotomic polynomial. Second cyclotomic polynomial. All right. So if I ask you phi 3, that is also easy. equal to 3.
X minus omega into x minus omega squared.
Okay, if I open up, what will we get? X square minus omega plus omega square x plus omega cube. And what is that?
X squared plus x plus 1.
And this we anyway remember from our previous results. I mean, previously we know that this is the irreducible polynomial. So there is one thing which I'm writing all the time, irreducible. Irreducible. This is one important fact. Look at n equal to 4. 5, 4. What is that?
X minus I into x plus I.
What is that?
X squared plus 1.
And this is irreducible, right? I'm talking everything over Q, okay?
Irreducible over Q.
Okay. All right. So this is how we get that these cyclotomic polynomial are in fact the irreducible polynomial over Q, which contains primitive nth roots of unity because they are being expressed as product of primitive roots, because they have been obtained by taking the roots and by writing the polynomial. So this is one important result that we have. Therefore, suppose we know now that given a primitive root, the degree of primitive root is nothing but the degree of the cyclotomic polynomial. Knowing this, can we get the degree of extension q zeta 8 over q? I think we will come back later. This will need some more thing maybe. Now, if we try to write, can we write the degree of nth cyclotomic polynomial? So if you see here, the degree is 2. Here is degree is 2. Degree is 1. In general, suppose I ask you that what is the degree of a nth cyclotomic polynomial? So what do you say?
Euler function pi of n.
Exactly right. And how do you get that?
Pardon?
Yeah, so how do you get that number exactly same as the degree is exactly same as the number phi n, Euler phi function?
Yes, proved in the class.
Proved in the class. All right. So good. Maybe I will recall one thing. So when you have a zeta, a primitive root, given one primitive root set, let's say, okay. Suppose you know that there exists one primitive root if you have n greater than equal to 2. In fact, for n equal to 1 also you have a primitive root. So for every n, you know that there is a primitive root. Like there will always exist one. And I want to know how many, because that many, whichever you have primitive roots, that many products you will come in your linear polynomial, and that will decide the degree. So decide a degree is being decided by number of primitive roots. Suppose you have one zeta as a primitive root, then how many other zeta can be primitive roots? Can you say that? Zeta prime, how many other?
The number of coprimes.
Co-prime to what now?
Coprimes to n.
Well, okay. So I should say this. I will explain now more. All primitive roots are just generators of this, right? Because once you fix one root, all roots are just the powers of that one primitive root. Now, among those powers, you want to check which are the primitive one. Since you know it is a cyclic group of order n, it's a cyclic group of order n. So among that, powers of the zeta, let's say power of order n elements, when does that generate the group? Only when GCD of n and I is 1, right? So if you have A as a generator of a cyclic group, then A power I is also a generator provided the GCD of order of A and the power of A is co-prime. Order is n, power is I. They should be co-prime. That means you have phi n number of, this is the degree. So answer is phi n, Euler phi function. This is okay, right?
Yes.
All right, so now we go to next question. We will come back to this question zeta 8. So let's do some more thing. Can we write irreducible polynomial for a primitive nth root of unity? If so, how? Irreducible polynomial Primitive nth root. So, okay, I think now we can do this question. So we want to know the degree, okay? We want to know the degree of this extension. In order to know the degree, we just need to know what is the degree of irreducible polynomial satisfied by a primitive eighth root of unity. And we saw that cyclotomic polynomial, eighth cyclotomic polynomial is nothing but an irreducible polynomial satisfied by a primitive eighth root of unity. This is okay, right?
Yes.
So now degree is okay, right? Now you can tell me what is the degree of Q zeta 8. That is degree of eighth cyclotomic polynomial, degree of eighth cyclotomic polynomial, which is the Euler phi of 8. Which is the Euler phi of 8, which is nothing but those n such that n and 8 are co-prime. And how many those? The cardinality, which is nothing but 1, 3, 5, 7. Degree is 4. And the cardinality is 4. Therefore, your degree of polynomial is also 4. So degree is very easily we can get it 4. Otherwise, you will keep doing that. This is same as q root 2 comma I over q and then degree was 4. Or you can write it is a splitting field of x square minus 2 x square plus 1. Or you can write it is a splitting field of the polynomial x power 4 plus 1. Same thing. This is irreducible. Huh? This is irreducible. And that you will get how? Let me go back now. Now for a prime, suppose I want to ask you for a prime. What is the degree of q zeta p over q? That is easy to tell now, right?
P minus 1.
Exactly, p minus 1. Because this is Euler phi function, phi p. So things have become so nice now once we know more theory about that. Okay, so I think this question is just a repetition of previous one. I think I will stop and I will discuss the two questions. These two questions are left. We will discuss, I think, these two questions in the next class. Yeah. Okay then. Thank you.
Thank you.
Yeah. Okay. I will stop recording.